So in the previous lecture, we solved a simple differential equation which corresponds to an exponential decay. And this was the differential equation. And what we showed was that this equation implies this particular solution, x of t equals x0 e to the negative beta t. Okay. And I'll just remind you that x is the concentration of protein. X0 is the initial concentration, also known as the initial condition, and beta is just a constant that defines how quickly the protein is being decayed. Alright, so now I want to graph what this solution is actually telling us and see if we can get some intuition. I'll draw that straighter. Okay, so I'm going to have t, or time, on my horizontal axis, and x, or the concentration of protein, on my vertical axis. And for this discussion, we're going to only consider the case when x is positive, because you need a positive concentration of protein. Mathematically, there's no reason we can't start with a negative initial condition for x, but we'll start with positive initial condition, and we'll just sort of impose that as a condition for this to actually relate to some physical system. Okay, so remember, at time 0, we're starting at x0, which I've just shown in green, and the dynamics are x of t equals x0 e to the negative beta t. So as t goes to infinity, what is going to happen to x? If you just think about our original problem, we had some proteins that were being degraded at some rate, and seeing as they're just going to be constantly degraded, if we wait a long enough amount of time, we would expect x to go to 0, and that's exactly what happens in this equation. If t goes to 0, or sorry, t goes to infinity, then e to the negative infinity goes to 0, and x goes to 0. So what does this mean? This means that for long amounts of time, we're going to end up sort of at low values of x. And essentially, we're going to exponentially approach this. That's what this equation is telling us. So I'm just going to draw, let's see if I can connect this, an exponential. That actually works pretty well. So this is our solution here, x of t. Okay. And notice that initially x is degrading quite quickly, but then over time the decay rate is slowing, and it asymptotically approaches 0. And why does this happen? Well, one way to think about it is to go back to our original equation, dx dt equals negative beta x. So one way to think about this equation, this original differential equation, is that it gives us the slope of the tangent line at each point in time dependent on x. So initially, at the beginning of the experiment, we have a large amount of x, relatively. So the slope of the tangent line is relatively low because dx dt is inversely proportional to x. So in other words, for high amounts of x, we have very negative values of dx dt. So that's what it means to be inversely proportional. So as the experiment progresses now, and the concentration of x is decreasing, the slope of this tangent line is now also decreasing. So that's why we have this negative exponential curve. And I almost hesitate to say this because this is so basic, but you can, if you just think of an exponential function, we'll just say e to, I don't want to say x because I already have x, but we'll say, we'll call this y. So e to the y is just a function that looks like this. E to the negative y is a function that looks exactly like it, but just going in the opposite direction. So this e to the negative y here is sort of loosely analogous to what we're seeing up here because beta is a negative parameter. So that's pretty much all I wanted to get across in this video. I just wanted to plot this out and show you what the concentration of protein is doing over time. And I guess the last thing that I should mention is that if we think back to our original system, and we just have a cell with some protein, and this is time equals 0, if we waited a very long amount of time, so for t much greater than 0 or t equal infinity, we'd still have the same cell, but now there would be no protein left. And that's exactly what that exponential decay function is telling us as t is approaching infinity, x is going to 0. So this makes sense conceptually, and it's just sort of mathematical fact. So anyway, I hope that these two videos have given you a basic understanding of simple exponential decay, and in the follow-up videos, I'm going to try to start applying this to more useful applications within system biology and computational neuroscience. Thanks.